charge collection. So if you look at the far observer at a distance small r, then instead of following the position of every charge, he can use instead a multiple expansion and describe a field in a systematic expansion in 1 over r. Yeah, so the first term in this expansion will be q over r. Then it will be the dipole moment, d times r over r cubed, and then there will be quadruple moment, qr squared over r to the 5, and so on. And every term is in this expansion is suppressed by more powers of a small parameter, which is big R over small r in this case. So if you are in the if you're sufficiently far away, what matters is typically the first term in this expansion, so the total charge of it. And then if you want to like refine your description, or if the total charge is 0, then you can add the dipole moment to get a better description of the fields. And then if you want an even finer description, you add in the quadruple moment, and so on. So the important point is here that for the far observer, even if that there is millions of charges in this little area, you can just use a few parameters like a total charge and the dipole moment and so on to describe in a completely satisfactory way the electric field in his vicinity. So this far observer, he could be an engineer. He knows nothing about effective field theories. Yeah, but like this guy from Moliere's, yeah, he actually discovers that he has been using effective field theory all his life. And that's one important point of these lectures, is that effective field theory is something that is very natural, yeah, that it comes at many different physical scales, yeah, from very small to very large, yeah, and it's just about simplifying the physical description of a system. Let me give you another example, yeah, from physics, yeah, that's where effective field theory is thinking is important. So if you're looking at a collection you're looking at an atom, and then there is a photon that is arriving at some energy, yeah, and is approaching this atom. So if this photon has a high energy, and that means it will probe small distance scales. If this is the case, yeah, then it will probe. It will look. The photon can peer inside an atom and see that the atom is made of positive and negative charges. So if you have a small distance scale probe, like a very high energy photon, yeah, you have to see. You can see each charge separately. On the other hand, if you have on the right hand side of the slide, if you have a low energy photon, then this low energy photon will just see this atom as a neutral object, and because photons do not interact with neutral objects, so in the first approximation, the photon will just ignore this, and it will go through it or go around it, yeah, as you like it. So here, depending on which scale we are at, which energy scale, or equivalently which distance scale we are at, we're seeing actually completely different physics. Yeah, and one for high energies, yeah, we see a strong or important rate of interactions between the photon and the constituents of an atom. And if you're going to low energy, then these interactions shut out, and you don't see, you see completely different kind of an object. So this is actually what happened in the early universe at some point. Yeah, that there were free charges, and then the universe was highly ionized, and photons were interacting with this highly ionized universe. But at some point, the electrons fell into protons and other nuclei. And once this happened, yeah, then the universe became transparent to the light, and now we see this light, yeah, from in the form of the cosmic microwave background. So if we go to particle physics or quantum field theory specifically, yeah, then this notion, yeah, of far away and large distance and small distance and large energy and high energy, we can actually make it more sharper. So consider a theory, a very simple theory, where we have a light field, light particle that we call phi, and we have a heavy particle, yeah, that we call h. And these two interact with each other, and we have this interaction vertex, yeah, between two particles phi and the heavy particle h. So now we are interested in this theory, in the scattering of two particles, so two light particle phi into, again, two light particle phi, which will be mediated by this heavy particle h. So if we look at it in the distance space, or in a coordinate space, yeah, then what happens is that if we are looking at, we can resolve the distance scales where x1 minus x2, that was the distance at which the field propagates, it's much smaller than the inverse mass of the mediator. Then we see the effect of the propagation of the heavy field. But on the other hand, if we go to large distance scales, yeah, because in the distance in the coordinate space, the propagator of a particle will die out exponentially at large distances. Then at large distance scales, we will not see any propagation of a mediator, and this will look like a delta function potential to us from sufficiently large distance. This is even more intuitive or simpler to represent, yeah, in the momentum space. In the momentum space, the propagator of a particle, yeah, is given by 1 over p squared minus m squared. So it will be 1 over p squared for at large energy, so it's at small distance scales, or it will be minus 1 over mh squared at small p squared, or so that means at long distance scales. So the situation where we have the large energies, yeah, is shown again on the left picture, and here we see the propagator we can resolve the propagator of the heavy particle. On the other hand, on the right hand side, yeah, we see the situation where we are at small p squared, and here we cannot resolve the propagator. The propagator looks to us like 1 over mh squared. So if we calculate the amplitude for this process in this energy regime, then what we see is this 1 over mh squared for the propagator, and this interaction becomes indistinguishable from a contact interaction between this light fields. So in quantum field theory, this is the basic mechanism how effective theory arises. Yeah? So because the propagator of a particle becomes just a number, just a constant at large distance scales. So the effects of the propagation look like contact interaction from if you're looking from sufficiently low energies, or equivalently again if you're looking from at sufficiently large distance scales. Yeah. So this is how we can see this analogy between large distance or far observer and near observer in the quantum field theory. And this is all about energy scales, yeah, momentum scales that are involved in the process. So all in all, yeah. So this is the important point, yeah, of effective field theories. Again, that if we go to low energies, things simplify. Instead of something moving in between these two light particles, yeah, we can describe effectively the same interaction just by getting rid of the heavy particle and just describing the same effect by a contact interaction between light particles only. And we don't have to ever mention and the heavy particle again to describe the physics. So in the more technical terms, yeah, we can replace the heavy particle by some polynomial interaction. Polynomial means that there is no 1 over a phi, or there is no singularities or anything, just phi to the 4th, phi to the 6th, phi to the 8, and so on. And this will give us the equivalent description of physics. So this is how the effective field theory will arise in all our examples in the following. So you could see that you could get to an effective field theory in 2 different ways. Yeah. So one is bottom up. Or maybe what I was describing was a top-down approach. In a top-down approach, we have a given theory, and then we move to a low energy regime of that theory, and then we can integrate out. So the procedure of getting to read the heavy degrees of freedom is called integrating out. And we integrate the degrees of freedom heavier than some prescribed mass scale. But we can also do another way. So we can just try to write down the theory. So starting from a bottom up, we don't know even when we don't know what the heavy degrees of freedom are, or we just want to remain agnostic about what is the high energy theory. We can just start with the light degrees of freedom, and then build the Lagrangian describing all possible interactions obeying some prescribed set of symmetries, and organize this Lagrangian in some consistent expansion. So both ways are actually used in practice, yeah, and I will try to illustrate them in a simple example in a following. So going back to this ladder, yeah, of the effective field theories that we can see in nature, let me give you an example that illustrates this ideas. And the simplest example that exists here is actually down at the bottom of the ladder. Yeah, so let's go to the bottom of the ladder where there is the least number of degrees of freedom. If you go to very low energies in nature, the only available degrees of freedom that exist are photons and neutrinos. And we'll try to illustrate these ideas, but by writing an effective field theory for the photons only. So let's forget about neutrinos. Yeah, let them just move in the space and not interact. And we are interested in the effective field theory of photons. So this effective field theory of photons is called Euler-Heisenberg theory, or I will call it Euler-Heisenberg effective field theory. The joke here is, of course, that neither the Euler is the famous Euler, nor the Heisenberg is the famous Heisenberg. Yeah, so Euler here in this is Hans Euler, who was he's not a famous mathematician, but he was a Luftwaffe pilot who died in the Eastern Front. And Heisenberg is, of course, not the famous Heisenberg from Breaking Bad, but a quantum physicist from Germany. What is the rules if we build an effective field theory of photons? So the rules that will be used in most of the examples in this lectures, yeah, is that we're starting with quantum mechanics, of course, and Poincare invariance, which gives us the framework of relativistic quantum field theory. So the degrees of freedom that we want to describe are this is a massless spin 1 photon, which, as every massless particle with spin 1, has 2 polarizations. And this means that if we want to describe a spin 1 photon in a quantum field theory, we need to add gauge invariance, U1 gauge invariance, that gets rid of this spurious degrees of freedom that would otherwise exist in a vector field. But then we will assume that this theory has some finite validity regime, and then we call this the top of this validity regime. We'll call it lambda. We call it cutoff lambda, And then there is no other mass scale than lambda. So then what we do, we write down a complete, so starting from these principles, we build the most general Lagrangian that is consistent with these principles, and we organize it in some expansion. Yeah, so we are interested in describing the theory at energies that is much smaller than this cut of lambda. So very, very, very low energy photons, and we can build the Lagrangian, yeah, in the following way. We first write down all dimension 4 terms, yeah, that you can make out of this out of the photon field. Then we make all dimension 5 the term, but then for dimensional reasons, yeah, we have to put this dimension 5 term in the Lagrangian has to be suppressed by 1 power of scale lambda. And then because the Lagrangian, the full Lagrangian has to have dimension 4. And then we can take again the photon field and try to build all possible terms of dimension 6. And then for dimensional reasons, yeah, we have to suppress this term by scale lambda squared and so on. So this at the level of Lagrangian, we have this clear expansion, yeah, in the dimensions of the consecutive terms in the Lagrangian, and the scale, yeah, that serves as an expansion parameter is called lambda. Why we're doing so? Because again, for dimensional reason, if Lagrangian is expanded in this way, then amplitudes, for example, if we calculate the amplitudes for scattering of 2 photons into each other, they also have to have this structure, yeah? Because the only scales in the problem are lambda, the cutoff scale, and the energy of the photon. So amplitude, again, for the 2 to 2 amplitude is dimensionless, so it has to have a form that it's A0 and plus A1 photon energy over lambda plus A2 photon energy squared over lambda squared, and so on.
Sorry, just a quick question. Could you please tell us what the dimension means?
Okay.
Thank you.
So fortunately, I cannot. Can I? Is there a place where I can write something?
If you go to the share screen link, you can make a whiteboard as one of the options that comes up. So you would have to unshare what you are sharing now, and then click again on share screen.
Yes. New share whiteboard. Can you see the whiteboard now?
Yes.
Yeah. So yeah. So excuse me. In that I should be saying that. Yeah. So in the Lagrangian, yeah, we build a Lagrangian from the photon field a mu, and this photon field has we assign it a mass dimension is energy, yeah, to the power of 1. So now, now, if, for example, if we have a like, let's assume that we're doing something terrible, yeah, and we adding in the Lagrangian a term like that. So we have 2 fields a mu with dimension 1. So this term would have dimension 2, and then since Lagrangian has mass dimension 4, we would have to add some power of lambda. So this is our scale, external scale in the problem that we just added by hand, and this is our field that describes the photon field, and this you have to if you have two of these fields, then you have to for dimensional reasons, yeah, you have to add 2 powers of lambda. So this is the idea of an expansion. Of course, this term we don't ever write because it would violate gauge invariance. Yeah, but if we write d mu a nu squared, so for example, something like that, which is the kinetic term, part of the kinetic term, then this has, there is two dimensions because the photon field, but also derivative has a dimension because it's 1 over, derivative is 1 over distance. So it's like momentum. So it has also dimension of energy. So all in all, we have dimension 4 term, and here we don't have to add any other scale. And this is how we will build the Lagrangian from the photon field, yeah, in this dimensional expansion. It will become a little bit more clearer as we go on, yeah, because I will try to give you more examples like that.
Oh, thank you very much.
Now, how do I kill it? Okay, I killed it. Now I have to share again. There is something in the chat which I didn't see. Okay, that's not me. And now I have to find again this my keynote presentation. Yes. Maybe if I do. Okay, so how do we build? So we're going to build the Lagrangian out of the photon field, and so in this case, actually things simplify because of symmetries. So because of gauge invariance, the only objects that we can use to build a Lagrangian in this case, we have only photon field, but we cannot write a Lagrangian with just a photon field because that would not be gauge invariant. We have the photon field always have to come in a specific combination, which is called the field strength. So this is what I wrote on the right-hand side. F mu nu is equal to d mu a nu minus d nu a mu. This is the gauge invariant combination of the photon field, and the Lagrangian, effective Lagrangian, has to be built out of this combination. So so that means that the effective Lagrangian has to be a function of f mu nu, and also another object which is just an auxiliary object which I called f mu nu twiddle, which is just a f mu nu multiplied by this by the Levi-Civita tensor. Now we also can use the derivatives, and we can use the scale lambda. So that already tells us that we can simplify our discussion because there's no way the odd dimensions of not odd powers of dimensions can appear in this Lagrangian, because f mu nu has dimension 2. It has 1 photon field and 1 derivative. So together the dimension is 2. So because we have to build our Lagrangian from the photon field, so it always has to be f the powers of 2. We cannot just add 1 derivative because 1 derivative would not be Lorentz invariant. It has to connect to something. So all in all, we can only have even power of it. So we already simplified our task by 50%. Actually, it turns out that it's even simpler. It's level. So at the level of dimension 2, if we want to try to build any invariant, yeah, from this field f mu nu, you can see that there is nothing that we can write that is non-zero, because the only thing that we can write from one field of mu, if we make it Lorentz invariant, we have to contract the Lorentz indices. But then if we contract the Lorentz indices of f, then we find that f mu mu is equal to 0, or the same with tilde f mu. So there is no invariance at dimension 2, so we can forget about the dimension 2. Now the next dimension that appears in this expansion would be dimension 4, and in this case we have one invariant that we can write, which is f mu nu f mu nu. So this is the only invariant, only non-trivial invariant that we can write at the dimension 4 with the available tools. Yeah, so that is we only use the field strength of the photon. So maybe you could protest, and you can there is other ways you could do it. Yeah, for example, you could write tilde f mu nu tilde f mu nu, but then by some algebra, simple algebra, one can show that this is the same as f mu nu f mu nu. So we don't have to write it. And there is another thing that you could try to write here is the f mu nu tilde f mu nu, but then you'll find that this term is a total derivative, and total derivatives, they don't matter in the perturbative Lagrangian, so we can skip them. And the final thing that you can try to write at dimension 4 would be derivatives of this f mu nu, but then it's again 0. So there's only one invariant. So at dimension 4, our Lagrangian has a unique form, which is f mu nu up to some number, yeah, that is convention, yeah, that we can choose it for our convenience, and the convention in this case is 1/4. That's so far so good. So we already built the Lagrangian, just starting from completely general principles, so gauge invariance and Lorentz invariance, up to dimension 4. But let's continue. So at this point, this f mu nu describes the kinetic term for the photon field. So it only describes propagation. There is nothing else. It's just photon propagates in the vacuum, and it never interacts. So let's try going beyond dimension 4 and writing some interactions. And if we go to dimension 6, it will again turn out that there's no way to write down any possible interactions. So f mu nu. So for example, if you try put three tensors, three field strands tensors f mu nu together, and contract the Lorentz indices, you find that this is 0. This is maybe not completely trivial, but yeah, if the first two f's are they form actually a symmetric tensor, and then you contract it with an antisymmetric tensor, and you're getting 0. So this doesn't work. Then again, derivatives don't work. You could write f mu nu box f mu nu, where box is D'Alembertian, so two derivatives together. But this term, this trivial, actually can be eliminated by the change of variables. So if you already have this dimension 4 term, and then if you change variables, like in the bottom right of the slide, say a mu goes to a mu plus some constant times the D'Alembertian a mu, then even if you write these 10 terms, you can eliminate it by change of variables. Since physics cannot depend on the change of variables, so any variables are good to describe the photon field, however you redefine it, it should be the same theory. That means that this term doesn't have any physical content. So again, we can skip it. So all in all, after you exhaust all the possibilities, you find that in this theory, also at dimension 6, it's not possible to write down any interactions between the photons that will obey our principles, yeah, which are very basic principles, gauge invariance and Lorentz invariance. This is another way of saying that also photons, yeah, they don't break the charge conservation symmetry. So we have to go to dimension 8, and then at dimension 8 we do find that there is a possible interactions. So at dimension 4 we had f mu nu as a possible term that obeyed all the rules. So if we just squared it, that it's also a legal term. So we can write f mu nu squared terms as a possible interaction with dimension 8. But it's not the only possibility. You can show that there is another way, another independent way to write this term is f mu nu tilde f mu nu. So this is an independent interaction of, again, between the photons. So I told you before that f mu nu, twiddle f mu nu is a total derivative, but if you square it, it's no longer a total derivative, yeah, because it's a square of a total derivative, but itself it's not a total derivative. So this is a legal term in the Lagrangian, and this the last term is in between. So we just take f mu nu, and then we take f mu nu twiddle, yeah. So then we take this two possible building blocks to put it together. And again, you can show that this exhausts all the possibilities. So whatever else you write, you can either eliminate it by change of variables, or show by some simple algebra that they are equivalent to the ones that we've already written. So if you write the effective theory for the photon up to dimension 8, this is what you get. Yeah, this is the Lagrangian, in the most general Lagrangian. So you have three parameters in this Lagrangian, which I call them C1, C2, C3, and three parameters in the EFT Lagrangian. They go under the name of Wilson coefficients. Yeah, usually with just a convention that we refer to them as the Wilson coefficients. On the other hand, we have the first term is a kinetic term, and the ones at the dimension 8, they describe interaction of the photon field. And that means that this is the so the interaction terms in an effective Lagrangian are referred to typically as operators. Yes, so the language that is used in AFTCI has this own quirks, and so again the strategies here is that we started with some symmetries and we try to write down everything that is allowed, and then we're getting the most general theory, which then we can confront with experiment. So what is this? What does this theory describe? Yeah, so this theory describes, first it describes of course the physics of lightsabers, yeah, because this tells you how light interacts with each other. Yeah, so this is very important, yeah, from the point of view of human culture. But except for lightsabers, yeah, it describes basically the entire textbook electrodynamics. So the textbook electrodynamics and the propagation of the electromagnetic fields is contained in this first term, f mu nu, f mu nu. On the other hand, this interaction terms, yeah, they describe new effects, yeah, that are beyond the usual, what you usually learn at school about electrodynamics, because they describe nonlinear effects in electrodynamics. Yeah, so you've been told that, of course, that electrodynamics is linear and it obeys this superposition principle. But this is true, but only in the first approximation. If you go beyond the leading approximation, then electrodynamics is nonlinear, and this nonlinear effects, yeah, then they can be measured. For example, one of the effects is so-called vacuum by refrigerants. Yeah, so you can describe the rotation of the polarization of a light, yeah, as it propagates in the vacuum, and this effect actually has been tentatively observed already in the lights from I think quasars or neutron stars. There was an astronomy paper a few years ago, yeah, that claimed that this kind of effect can be observed. So this interaction terms, yeah, they describe real effects, yeah, that can be measured in nature. I mean, all of these effects, yeah, are I mean, the first, maybe let me say this a little bit later. No, not too mix. So another important point that I want to make about this effective field theory, yeah, is that it actually describes this is something that you can calculate with. So you can calculate all possible processes. You can also calculate, of course, classical processes, classical propagation of waves, but you can also calculate in quantum physics. And you can calculate the scattering of the two photons with, you applying the usual rules of quantum field theories. You start with this interaction vertex, and then you're getting some form of the vertices in the theory, and you can calculate it. So, for example, if you calculate the photon scattering with some given polarization, this is the results that you're getting are on the bottom of this page. So for photons of the same polarization, you're getting the result proportional to s squared t squared plus u squared, where s, t, u are sorry, there is a typo at the end. Are Mandelstam invariants, and different configurations of this polarization will give you a different amplitude. So you could try to measure this coefficients C1, C2, and C3 just by looking at the light by light scattering with different polarizations. And as far as I know, this kind of experiment has not been done yet. So people are thinking about it to have sufficiently strong lasers, to be able to observe it. But as far as I know, this effect has not been observed in the validity regime of the EFD. So light by light scattering is something that happens. It happens routinely at high energy colliders, and this of course has been observed. But this is at much higher energies, where you produce new particles, and you produce resonances and so on. In the low energy theory, where this A effective field theory works, is not this effect has not been observed. And that one last thing I want to show: if you calculate this amplitude, you find that the amplitude is different for all polarization plus 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 and polarizations minus 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 minus. So the difference is that the contribution of this C3 operator, or the C3 Wilson coefficient, flips the sign between the two amplitudes, and that means that this effect of this operator violates parity symmetry. So because you're getting a different result, for positively scattering of positively of helicity plus photons and helicity minus photons. So of course, if this effect existed, that will be a huge discovery. There is now at the moment no indication that this kind of effects are present in nature, but we never know. So now another thing that I want to stress, is that if you want, this is again the completely healthy quantum field theory. So instead of, apart from calculating tree-level diagrams, you can also calculate loop diagrams in this theory. So I will not be calculating loop diagrams here, but in principle this is possible. And there is an important difference between the usual theories that we are used to. If we calculate this loop diagram that is shown in this picture, we'll find that this is divergent. And if we use dimensional regularization, just by again dimensional analysis, we can show that this diagram is proportional to 1. This 1 over epsilon is the dimensional regularization parameter, and because we have two different vertices here in this diagram, the result has to be proportional to 1 over lambda to the 8, and then by dimensional analysis it has to go like energy of the photon to the power of 8 also. Now so now we want to cancel this divergent by some counter term in a quantum field theory calculation. But the point is that none of these terms that is already in the Lagrangian can serve as a counter term, because they actually depend on photon energy as energy to the 4th. So you have to add to cancel the divergences that are produced that appear at one loop level. You have to add a new term to the Lagrangian, which will be something like the one shown here with the proportional to D1. So this means that this theory is not renormalizable in the usual sense, because if you truncate the Lagrangian at a given order, this will not be completely, in a theory, there will be always divergences. So you cannot cancel all divergences of a theory with a finite number of coefficients in the Lagrangian. You always have to add more and more operators to provide you counter terms to cancel the divergences. But the theory is still normalizable in the sense that every divergence that will appear can be cancelled by some counter term. You just have to include more and more of operators in your Lagrangian if you want to go to higher and higher orders in the loop calculation. So as long as you're interested in some finite precision, so if you're willing to truncate the Lagrangian at some finite order, like for example 1 over lambda to the fourth, then you don't have to worry about this, because all these divergences will appear at larger orders, or if they appear at the order 1 over lambda fourth, you will be able to absorb the divergences into the parameters of the Lagrangian. So this issue, of renormalizability, it's used to be people thought that it's very important for a theory to be renormalizable. Now this view has changed a bit, or it has changed completely. That renormalizability of the theory is not an important ingredient to have to be able to produce useful predictions. What is important, is that as long as you have some consistent expansion and you have some criteria when to drop when the higher order terms in the effective field theory expansion, then this problem of non-renormalizability is not relevant for practical calculations and for making the predictions. So let me just finish. Is this example of Euler-Heisenberg EFT about changing a little bit perspective. And so now, so far, we have written the effective Lagrangian just starting from the bottom up. So just starting from the particle content and the symmetries of the theory. But what is the meaning of these operators, of these higher dimensional operators? What do they actually describe? What kind of more fundamental physics do they describe? So of course, we know that in QED, if you go to higher energies, above the validity of the EFT, this kind of four photon interactions do exist because we can exchange, for example, a loop of electron, and this will effectively give us an interaction between 4 photons. So now if we calculate this loop in an EFT, we're getting a result something like that. We're getting the result of this that we see on the left-hand side of the slide. That for different polarization configurations, we'll get some dependence on the Mandelstam invariance of the scattering process, and then we get if up to some corrections that are small if we are at energies below the electron mass. If we compare the result in the QED that we can obtain in the QED to the results that we can obtain in an EFT, the two results have the same form, in the sense that the dependence on the Mandelstam invariant is exactly the same. So the EFT describes the same physics as QED, except that in QED, this Wilson coefficients C1 and C2 and C3, they take specific values. So you can match the amplitudes in QED and an EFT to find what Wilson coefficient will arise if the UV completion of this EFT is QED. And then you know that there is some answer. So C1 is alpha squared over 90, and C2 is some funny number that appears also proportional to alpha squared, and C3 is 0 because C3 would break parity and QED doesn't break parity, so C3 cannot arise in QED. So so the lesson here is that this dimension 8 operators, they describe real effects that happen in QED due to exchange of a electron loop between different photons. Yeah, so the virtual electrons, they lead to effective interactions between the 4 photons that you can capture in this effective field theory. But this is not the only possibility. So we know, of course, we have electrons, so this contribution does exist, but there can be other contribution. For example, we can have axions. Axions, they do couple to photons in a typical theory, and they can be exchanged between the photons. Or more generally, we can have axion-like particles that couple, like in this Lagrangian. They couple to f mu nu, and they couple also to f mu nu tilde f mu nu. And then the tree-level exchange of this axion will lead to again effective interaction between the 4 photons. So they will contribute to some scattering between the photons, and again will contribute to these effective operators in the Euler-Heisenberg Lagrangian, but with a different pattern than what was predicted in the QED. So of course, so this means that it still would make sense to measure precisely the Wilson coefficients of the Euler-Heisenberg Lagrangian in some controlled experiment, either in some astrophysical experiment by looking at how the polarization of starlight of quasars or something like that rotates, or maybe by some more controlled laboratory laser experiments, because this would allow you to exclude the large contributions from axions or from axion-like particles to these Wilson coefficients, and that again would be able to constrain new physics beyond the standard model this way. So this effective theory, so calculation in this effective theory can make sense. It can have actually important lead to some important understanding of also of fundamental physics beyond just QED. Okay, so let me stop this example of Euler-Heisenberg EFT. Is there any questions that was something that was so unclear here that you would like to clarify it at this point? I see some raised hands, but I cannot.
I guess, Adam, I would like to ask a question just for the axion. If you could go back this one slide.
Yes.
So the cutoff scale there is then given by the product of the F and the M, right? I mean, so it doesn't matter that the axion is perhaps very light. You can still have a very high scale, yes?
Yeah. So normally we associate lambda with the mass of this particle, but this is not always true. If there is another scale in the UV theory, like exactly is the case of axion, that you have 2 scales F and M, this lambda can be some combination of the 2, and this is the case in this case.
Right.
Yeah. So the answer is written that lambda is a square root of F axion and M axion.
So in this case, you would want the square root of the product to be smaller than the electron mass, or that wouldn't play a role for you?
Well, so that would be the most that would be the best, of course, because it's not only this square root, but also the coupling constant G, that matters, So all of these things together matter, How observable is this effect? But of course, you would like this effect to be larger, than the one in QED to observe it. But note, for example, that if you have axion-like particle that has both CP conserving and CP violating couplings, it could actually lead to an effect that is 0 in QED, this C3. And that could also so then even if it's smaller, and then if it's very small, this is something, this parity violating effect might be possibly observed in experiment.
Mm-hmm. Thank you.
if there's no more questions, yeah, then let me continue to the next topics. Yeah, so I went to the top of this. Sorry, I went to the bottom of this ladder. Yeah, to understand, yeah, the structures and the philosophy of the effective field theory. But now let's go back up to energies of the order of 100 GeV, 1 TeV, and this is a energy scale, yeah, where we have different kind of degrees of freedom, yeah, except for the photons, yeah, we also have W bosons, Z bosons, gluons, quarks, leptons, and the Higgs, yeah. So this is a completely different effective theory. And this goes under the name of SMEFT or SMEFT in short. And this here the rules are different. Yeah. So first of all, yeah, then the main way we approach this theory is bottom up, simply because we don't know the UV completion of that effective field theory. Second thing that is different is that the different thing here is that we have a different set of degrees of freedom. We have a different gauge symmetry because now it's, instead of U1, it's SU3 cross SU2 cross U1. We have a new element, which is spontaneous breaking of the symmetry down to SU3 cross U1. So these are the new things, yeah, that happen that we have to take into account when we build this SMEFT. But otherwise, the philosophy is the same. So we start with these rules of the game, so the symmetries and the particle content, and we build the most general effective Lagrangian in an expansion in some power 1 over lambda. So yeah. So let's start, yeah, with dimension. So what happens here if we start with this expansion? So at dimension 2, unlike in the photon case, we do have a possible term, because Higgs has dimension is a bosonic field. It has dimension 1. So if you take two Higgs fields, H dagger H has dimension 2. So it's possible to write down starting from the standard model spectrum, it's possible to write a gauge invariant term that has dimension 2, and this is H dagger H. And this introduces a small issue, yeah, to our thinking, because the idea was that we have this one scale, yeah, that controls our EFT. So this dimension 2 term should be proportional to the scale lambda squared. And we think of this lambda in this context as some large scale, maybe 10 TeV, maybe 100 TeV, maybe even 10 to 15 GeV. But this expectation is not borne out, because we know from experiment or that this term has to be much smaller than this large scale. So we write it as mu h squared as lambda squared, and the mu h is something of the order of 100 GeV. So if lambda is 100 TeV, yeah, then it's 10 to minus 6 suppression of this term compared to naive dimensional analysis. Yeah, if this lambda is 10 to 16, yeah, then this is like some huge suppression. And this, why this suppression appears here, we don't know. This is like this breakdown of our dimensional analysis of our philosophy. And we call it the hierarchy problem, and this has no solution so far. And yeah, maybe we will never know. Maybe this is just how it is. But let's forget about this problem. I will not discuss hierarchy problem at all in these lectures. Let's continue the expansion. So at dimension 3, there is nothing we can write. Yeah, so there is no way we can take the fields of the standard model with the gauge symmetries and write down a Lorentz invariant and gauge symmetric operator out of these fields. So there is nothing that's simple. At dimension 4, if we write everything that we can, this is displayed again in this slide. So we can again write, like before we had F mu nu, now we can write V mu nu, which is the kinetic term for the for the gauge fields that we have in the standard model, which is hypercharge and the SU2 gauge field and the gluons, which I call GA. There is one more possibility we can write in this Lagrangian, yeah, which is very interesting from the point of view of CP violation, is that we can take the gluon field and write this theta term, so-called theta term, G mu nu twiddle. Again, this is a total derivative in the Lagrangian, so we would, before we would neglect it. However, in QCD, it contributes via instantons in the path integral, and it cannot be dropped. Yeah, it's a topological term. Yeah, that has physical contributions. So we write this. We write this term in the Lagrangian. And then the rest, this is the F, G mu, the F, this is the kinetic term for the fermions, and they also contain, by gauge invariance, they also have to contain interactions of the fermions with the gauge fields, so the usual gauge interactions. Then at dimension 4, we still can write, so we can still write fermion Higgs. So this is dimension 4 term that describes the Yukawa interaction between the Higgs boson and fermions. And then finally, in the last line, we have a kinetic term for the Higgs and the Higgs quartic potential. Most of this term, so this is all we can write. And then a wonderful tribute, yeah, to this power of this EFT thinking is that actually all of these terms seem to be borne out in nature. Most of these terms seem to be borne out in nature. So we have evidence, experimental evidence for most of them. All the free parameters that appear here, there's 19 physical parameters, 19 Wilson coefficients, yeah, that appear in this Lagrangian at dimension 4. And we measured most of them, 18 of them, with a very good precision. The last one, this theta parameter, for some reason, is much smaller again. We haven't seen it yet. We have only a limit, yeah, that it's smaller than something like 10 to minus 9, maybe 10 to minus 10, depending on how you do this, treat this hadronic uncertainties involved. So, but in general, yeah, this thinking is that we take the fields and we write everything that is allowed by gauge invariance and Lorentz invariance. This thinking is again quite spectacularly borne out in nature. Yeah, so that all of this, or most of these interactions, yeah, are indeed present there. So let's continue. Let's continue this effective field theory thinking and go beyond this dimension 4. So up to dimension 4, this was, of course, what is known as the standard model. But we know that standard model is not the whole story. Yeah, there is something more than the standard model out there in nature. So let's apply this effective field theory thinking to the end, and also include dimension 5 and dimension 6 and dimension 7 and dimension 8 and so on term. Yeah, and this standard model together with this higher dimensional terms is known as the standard model effective field theory, or SMEFT in short. And at each order, yeah, we will include complete set of operators that are allowed by the symmetries. So let's start with dimension 5. And this is very, very, very nice and simple, because again, this dimension 5, there's only one possible class of operators that we can add to the Lagrangian. They are called Weinberg operators, like many things are. There are many Weinberg operators in literature, but this is one of them. So this LH, LH. So this is gauge invariant, yeah, because we are multiplying together two SU2 doublets, a lepton doublet and the Higgs doublet, and then we have to put two of them, yeah, because we have to have two fermions in this interaction. So this term. Let's add it. So we add it to the Lagrangian. This is the only thing we can add to dimension 5. As when Higgs obtains the vacuum expectation value. So on the right-hand side of the slide here, you have the Higgs vacuum expectation value. Lepton doublet contains the neutrino on the up and the electron on the down, or more generally a neutrino and a charged lepton. And if once you write this, once you include the vacuum expectation for the Higgs, this term leads to so-called Majorana neutrino masses. So neutrinos couple to themselves, so there is a bilinear term in this neutrinos. So this term is apparently has been so this has been observed in the early 2000s, or also the hints that of its existence they were coming for many years, probably for 30 years earlier, but this was finally pinpointed in the early 2000s. Of course, there is a small doubt whether we are observing this term or something else. Maybe the what causes neutrino masses is not this term, but Dirac, so-called Dirac mass terms that involve a new degrees of freedom. So except for the neutrino, you're also adding a sterile neutrino and then couple them together in a mass term, and that will be also could explain the observed results on the neutrino oscillations. But let's discard this possibility for the sake of the argument, and let's say that this what has been observed in the neutrino oscillation experiment is the neutrino mass coming exactly from this term. And you see that again we have a spectacular success of this effective field theory thinking, because again we started with this field content symmetries of the and we just adding everything that is possible in a consistent or expansion in some parameter 1/λ, and lo and behold, after doing that, the next to leading term after the standard model, the next term in this expansion is indeed what has been in nature. So this is a huge triumph of the effective field theory thinking, or the huge triumph of SMEFT. Of course, what I'm saying is a bit ahistorical, because when neutrino masses were observed, a few people were thinking in these terms. People were thinking more about some fundamental theories and string theories and so on. The mindset was a bit different, and somehow this observation that the d=5 term is what you expect, where this is exactly where you expect the standard model to break down, was maybe not stressed enough. But this is how you can interpret the historical facts, maybe a posteriori, that this is indeed a triumph of the effective field theory thinking. You write down everything, and then in a consistent expansion, and then we see dimension 4 terms, we have seen them long ago, and then the next thing we see is the dimension 5 term in this effective Lagrangian. So we even know now much more about neutrino masses. So we know that there is this what we measured more precisely. We haven't measured the scale of neutrino masses, but if there is no conspiracy, the neutrino mass difference squared, which are measured in oscillation experiment, are more or less the same as the neutrino masses. And then that means that the neutrino masses are in the ballpark of 0.1, 0.01 EeV. Again, there is some ambiguity whether there's normal ordering or inverse, but now there is data are pointing more and more towards normal ordering. So the fits work much better with the normal ordering. So let's not complicate things here. So we have this mass scale of neutrinos, and now if you translate it into this lambda scale in the effective Lagrangian, we find that lambda over c has to be of the order of 10 to 15 GeV. So that means that if we assume that C are order 1, so we like order 1 parameters in the Lagrangian for aesthetic reasons, then it means that lambda is the huge scale of 10 to 15 GeV, which means that this expansion parameter in the SMEFT is huge. Yeah, it's 10 to 15. So the next term in this expansion will be suppressed by 10 to 15 squared, and it will be very difficult to see, maybe other than in baryon. The only other experiment, apart from neutrino experiments, that would be sensitive to this higher dimensional terms, that would be probe maybe dimension 6 terms, are proton decay experiments. Yeah, so that is if lambda is indeed that high, that is indeed a conclusion. Yeah, so if you take this data at face value, if you really think in an effective field theory way, and you think that there is no conspiracy, that what you should do with your career next. Yeah, so then the best thing to do is, of course, work on neutrinos. Yeah, because we are further exploring this dimension 5 terms in the Lagrangian. So you could another thing you could work is on proton decay. Yeah, this is hyper-Kaviokande. Yeah, or of course you can go work in a bank, and I heard that Medallion is hiring now. So that would be the opportunities. For the rest, there is nothing because of this huge scale in the Lagrangian, in the effective Lagrangian. You don't expect to see effects of physics of this high dimensional term anywhere else, including the CP violation and electric dipole experiment. So this is the conclusion if you take the data at face value. But of course, yeah, we don't want to do that, yeah, because that conclusion is logical but too depressing. And there is a way out. Yeah, so the point is that this dimension 5 terms are somewhat special, because like all odd dimension terms in this effective Lagrangian, they violate lepton number. So it is possible that new physics violating lepton number is indeed at very high scale. The new physics violating lepton number comes at dimension, at 10 to 15 GeV. However, there is also new physics that doesn't violate lepton number, and it comes at lower scale, maybe at 10 TeV, maybe at 100 TeV. And in that case, this expansion of the SMEFT has to be modified a bit, like in the bottom of the slide. So all the odd dimension terms will indeed be suppressed by this huge scale of 10 to 15 GeV, but then this is like a double expansion in 2 parameters, lambda L, which is huge, and lambda, which is hopefully smaller, and it controls the expansion for the even dimension operators. So for the rest of these lectures, this will be our working assumption, yeah, because not because it's strongly motivated by the data, but it's because the alternative is very depressing. And let's assume that there is this double expansion in the active field theory, and that lambda is much smaller than lambda L, because yeah, that will allow us to see some other effects, yeah, of higher dimensional operators other than neutrino masses and the proton decay. So if we go to the dimension 6 terms, then this is where a lot of new effects appear, yeah, and this is also where all hell breaks loose, yeah, because while the dimension 5 we had just one class of operators that led to the ones that led to neutrino masses, at lambda, at dimension to the 6, yeah, we have thousands of operators, literally thousands, if you include the flavor structure, yeah, so if you allow for the non-trivial flavor structure, we have many different operators, and it's becomes a little bit it's difficult to actually control this, yeah, where this new physics effects can come from, yeah. So there's so many operators, yeah, if you want to use them, yeah, to fall asleep, you can count instead of counting ships, you can count the operators, yeah. And I assure you, this is a very efficient way, yeah, to fall asleep. So I will not talk about the dimension 6 now. Is the question? Do you want to ask a question? Oh, sorry. Okay, sorry. I will come back to dimension 6 operators in the next lectures where I talk about CP violation. So we will just focus on this with some like spotlight of the CP violation rather than looking more generally. But let me, in the end, for the end, talk about a bit different topic. Sorry, so do I have 15 more minutes, or should I stop now? What's the plan? Because
well, you have 15 more minutes here.
Okay. So in the last 15 minutes, I wanna talk about another ladder, or another step of this ladder, which is the effective theory below the electroweak scale, and this is also important, for all sorts of phenomenology. So this is something that I call weak EFT or WEFT in short. And the point is very, very simple. That in the standard model or in the SMEFT, we have the W boson or so on. But for example, if we are discussing muon decay in this theory, muon decay, muon has a mass of about 100 MeV, and this is the momentum transfer in this diagram is of the order of the muon mass, and it's much smaller than the W boson mass. So if you, for example, look at muon decay, you don't see the W boson. The W boson doesn't exist really for muon decay. What exists for muon decay is effectively this W boson propagator is contracted to a point, and instead muon decay proceeds by this effective interaction between 4 fermions, between between muon, electron, and the 2 neutrinos. And this point of view is not only more simple, so you get rid of one particle, but it's also much more powerful from the calculational point of view. If you're trying to calculate muon decay or any low energy processes in a full standard model or in the full SMEFT, you're actually running into problems as soon as you leave the tree level. If you go to loop level, you will find that your amplitudes, your results will depend on the logarithms of MW over MU. And logarithm of MW over MU is the parameter of the order of a few, and that makes your convergence of your perturbation theory much slower. Instead, if you're working with an EFT, with this contact interaction of mu and between the muon electron and the neutrinos, you never encounter this large logarithm because there is no W. There is no W in this theory. There is never an opportunity for the logarithm of the W mass over something to appear. So this theory is superior calculationally, and this is an important point, to the full standard model. Even though it's non-renormalizable, if you want to make precise calculations, you would rather go to an effective theory and get rid of the W boson. So what we do, let's go to this energies below 100 GeV. At this energies, W, Z, and Higgs top and do not propagate can be integrated out from the theory. And the weak and Higgs interactions are mediated instead by, there is no force carriers for these interactions, but instead they are mediated by effective contact interactions between the light degrees of freedom, like leptons and quarks. And this effective theory goes under the name of weak EFT here. I call it WEFT, but you can see also other names like LEFT and WET in the literature. So all these names refer to the same thing. And this is the same, again, the same thinking here as before, as for Euler, Heisenberg, Lagrangian, or for the SMEFT. So we're starting with some degrees of freedom. In this case, it's gluons, photons, 5 quarks, 3 charged leptons, and 3 neutrinos. And we we adding to it a symmetry principle, which is SU3 cross U1 gauge invariance, and we're building all possible interactions based on this that are compatible with these principles. So now the effective theory will be an expansion, yeah, when the scale lambda that is identified with, because we know in this case we know what the cutoff scale is. The cutoff scale is of the order of MW. So the scale lambda will be, you think a bit of it as something of the order of MW, and you build the Lagrangian as an expansion in the scale lambda, starting with this d equals 3 terms, d equals 4 terms, d equals 5, and so on. And you at each step you write all possible terms that are possible operators that are consistent with this with the principles of that you started with the symmetries and with the degrees of freedom. And again, this is now a big industry to enumerate all these operators. So again, for example, for at d equals 3, it's very simple. The only operator that appears here is the only operator that you can write down in dimension 3 is neutrino mass. At dimension 4, again, we have all this kinetic terms and so on. At dimension 5, we have dipole terms. That's something of interest for you. So both for the neutrinos and for the lepton and quark fields. And then we have all this thousands of terms at dimension 6, yeah, that come in all these possible shapes and flavors. So I will not again discuss all this theory. Let me just focus on a very, very small part of this theory that involves the interactions between the leptons and quarks, the contact interactions between the leptons and quarks. So if you in the high energy theory, this kind of interactions again are the charged current interactions are mediated by the W boson. But if you integrate out the W boson, all that is left from this is this contact interaction between the up quark, down quark, electron, and the neutrino, and of course between all different combinations of quarks as well, and leptons. Yeah, so there's many more of them. Yeah, I will just focus on this small subset of the interactions. Yeah, which is the up quark, down quark, electron, and neutrino contact interactions. So how do they appear? Yeah, how do these interactions appear? Yeah, so now we can use the top-down approach. Yeah, because we have the we know the high energy theory that the theory describing the interactions at the electroweak scale is the SMEFT. So now we can go down and derive what are the interactions in the weft. So there is several possible contributions actually to this contact interaction that can arise in the low energy theory that is the weft. So if you're starting with the SMEFT, you have this kind of, for example, you have these operators that are written down here in the middle, on the top. This is the dimension 6 operators between the Higgs and the quarks and between the Higgs and the leptons. When you insert the VEF of the Higgs, this covariant derivative contains a W, and one effect of this operator is that it gives you a new contribution to the W interactions with the electron and the W interaction with the quarks. So you in the SMEFT you can modify the coupling strengths of a W to leptons and the coupling strengths of a W to quarks. So now when you integrate out the W, this modified coupling strengths can actually carry over and to the effective theory, and you're still getting the contact interaction between the leptons and quarks, but the coupling strength or the Wilson coefficient of these interactions can be modified compared to the expectation from the standard model. So this coupling strengths will depend on what are the operators in the dimension 6 level of the SMEFT. So for this reason, you don't know what is the a priori, what is the coupling strength, what is the interaction strength in this vertex. This is something you have to measure from experiment, because even you cannot take standard model for granted. They might be dimension 6 operators, and they might modify the value of this Wilson coefficients in the weft. But there is more. There's actually there is something that the point is that the SMEFT might produce something that doesn't exist in the standard model or in the first place, or that doesn't would not appear if the standard model was the correct theory. So for example, for the SMEFT, you can have a different kind of dimension 6 operator where the Higgs interacts with right-handed quarks. Again, this requires a bit of checking that hypercharges and all the SU2 quantum numbers are okay for this operator. So again, if you Higgs gets a VEF, the covariant derivative in this operator will contain W boson, and it will lead to the W boson coupling to the right-handed quarks. Yeah, so something that in the standard model doesn't exist. So now if you integrate it out, if you integrate out the W boson, then this fact that the W boson couples to the right-handed quark will lead to a new operator in the weft, which describes the contact interactions between the leptons and right-handed quarks. So if standard model was correct, weft would only contain interactions, this contact interactions between left-handed leptons and left-handed quarks. But in principle, you should include in your phenomenological analysis also this possibility that there is an interaction that concerns the right-handed quarks. So that's another possibility, yeah, that comes from the SMEFT and leads to a new kind of interaction in the low energy effective theory in the weft. And then there is a third possibility that is in the SMEFT you can also mediate charge currents without the W boson intermediary. So there is a certain number of 4 fermion operators in the SMEFT which give you this contact interaction between the quark and leptons, and that will lead to charge currents. And those the interesting thing about them is that they lead. Some of them they lead to the structure of the that is exactly the same as in the standard model. So left-handed leptons, left-handed quarks. But some of them lead to a completely different tensor structures, like there are tensor interactions and there are scalar kind of interactions. So all these interactions can appear in the weft and should be taken into account in the phenomenological analysis. So all in all, if you look at in the weft at the interactions between the leptons and the quarks, the most general Lagrangian at the leading order is the following. Yeah, so it is a dimension 6 Lagrangian. It has 1 over v squared suppression, because this is the sort of the cutoff scale of this EFT. And here we have interactions between the leptons and quarks with several different tensor structures, and there's 5 of them. So I call them v minus a, v plus a, tensor scalar and pseudoscalar. And in a low energy analysis, in a phenomenological analysis, yeah, you want to include them all. Now you can also make a map, yeah, between the low energy effective theory, which is weft, and the high energy effective theory, which is SMEFT. So the interactions in the SMEFT and the interaction in the weft, yeah, they map into each other. So if you can relate the parameters in one theory to the parameters in the other theory, and at tree level, the mapping, the dictionary between the parameters is just shown here. And the important thing is that you see that if you use an effective field theory, you're getting some simplification, because you have many, something like a dozen of operators in the SMEFT, which reduce to something like just 5 different parameters in the weft. So not only your theory is more stable perturbativity if you use this weft instead of SMEFT to do the calculation, but also the number of parameters is smaller. So this I wanted to show you one more step of this ladder when you go with the Swift to even lower energies where hadrons appear. But of course, yeah, I see that the time is over, so I will stop now, and I will leave that that part to for the next lecture. But the message, the big message is that everything is the effective field theory, and then there is this. We have this hierarchy of effective field theories. We have this ladder of effective field theories. One effective theory goes into another effective theory, and they all connect to each other, yeah, and they are all parts, yeah, of the same physics description, yeah. And this is wanted to show it here in the last slide, yeah, that this looks like something, yeah, from that you have in the Eastern culture. Yeah. I leave you. This is a pretty picture, so I leave you with a pretty picture. Thank you.
Okay, so thank you very much. Maybe we have 5 minutes for questions, if there is any. Oh, there are 4 hands. Oh, no, these are claps. Yeah, I will clap myself. Oh, there are 2 hands raised. Philippe.
Adam, thank you very much for that comprehensive summary on effective field theories. I was wondering, looking at these Wilson coefficients, you seem to make always a distinction between the different quarks, but not though for the leptons. Is there a reason for that, or is that just more general?
No. So this effective theory contains everything. Yeah. So you have you can see that you have each field, yeah, in this list. It has a flavor index. Yeah. So everything is there. Yeah. I wanted only to focus on a very small subset because that's something I will need for the lecture on Thursday. Yeah. But yeah, there are interactions. There can be interactions that violate also lepton flavor. There can be
measured, it could be there.
Yes, and that's actually something that I'm studying now, using, for example, experiment at CERN. Yeah, well, so yeah, these things might exist, and these things are being looked for, yeah, in experiments. Yes.
Thank you.
Okay, there is one more question by Cornelis.
No, thank you. So when you say that everything is an effective field theory, do you mean that in principle interactions that we think of as fundamental, for example, the interactions in QED, might be an effective emerging phenomenon based on some theory involving potential particles that we don't know exist?
Yeah. So first, for example, QED. Yeah, we know that QED is not a fundamental theory. Yeah, because there exist more fundamental interactions. Yeah, at least those of the standard model. If you integrate out the heavy particles, yeah, at the energies, yeah, where at low energies, you get in QED plus higher dimensional operators. Yeah, so let me give you an example. Sometimes people say that G-2, yeah, is a huge triumph of QED. Yeah, so because yeah, QED can calculate G-2 to the 10 to minus 10 precision. But to actually get to this 10 to minus 10 precision, you have to go beyond QED. You have to include the fact that, yeah, there are some higher dimensional operators that you get from integrating out the other fields in the standard model. Yeah, so there is, as far as we know, at this point there is no fundamental theory. We don't know fundamental theory. Yeah, there may be some fundamental theory at some very high energy scales above the Planck scale also, but we don't have any glimpse of fundamental theory. And what we look at, the theory that we are working with now in practice are all effective field theories, and they are just embedded one into another. Yeah, they form this hierarchy. Yeah, there's like they are like matryoshkas. Yeah, they one go into the others. But we don't see the top. We don't see the top of this pile. Yeah, even on the top, yeah, the standard model is also an effective theory, as proven by the existence of neutrino masses.
Okay, thank you.
Okay, there is one more question by. Okay, I don't know who comes first. Pierre.
I think it was Klaus first, but okay, I saw his camera
Pierre,
before.
go ahead.
Okay, no problem. So, well, first, it's a remarkable lecture, so thanks a lot, Adam. I'm coming back to your depressing perspective. You said, in fact, the next physics scale is 10 to the 15 GeV. And so the rationale to look for these subtle effects are small coupling constants, or can you elaborate a bit on that? I didn't get that very well.
Yeah, so there's two rationales. Yeah, so you could say that the scale lambda is not really 10 to 15. It's this is what you're saying. Yeah, that it's a mirage. That in fact there is really this coupling constant C is small. Yeah, so maybe it's 10 to minus 10, and then this lambda is just the 100 TeV. That's one possibility. That there is some small couplings in the UV theory, and that's a possibility. That's a very, very good possibility. But there's another possibility that I was trying to explain. Yeah, that the point is that or maybe let's look at this. These interactions on dimension 5 are very special because they violate lepton number. And it might be that lepton number, yeah, is for some reason a good symmetry, yeah, also of the UV completion of the standard model, yeah, so that there is only physics at the very high scale is allowed to violate lepton number, while the physics at lower scales is not allowed to violate lepton numbers. That there is the lepton number is a symmetry of the. And then it means that only physics at the very high scale produces the dimension 5 operators that we have seen, but then physics that produces dimension 6 operators, which can be lepton number conserving, can be at lower scale. Yeah, so there is a possibility, yeah, that what we see is not really the nearest new physics, but it's the new physics, yeah, that with the special properties that appears at very high energies. But there is another new physics that conserves lepton number, that doesn't violate lepton number, that enters at low energies. And this new physics would produce dimension 6 operators suppressed by a lower scale than 10 to 15 GeV. And then this would correspond to this expansion where we have these two scales that I call lambda L. Lambda L is 10 to 15 GeV, and it suppresses d equals 5, d equals 7, d equals 9. And then there's another scale, lambda. This is the scale of this other lepton number conserving new physics that suppresses the operators d equals 6, d equals 8, and so on. So that's the thinking, and that is more.
Okay, that's very clear.
Optimistic, yeah.
Thanks.
Okay, Klaus, please.
Yeah, maybe just before I ask my question, one more comment, because here you made before you came to that, you made another assumption that the d equal 5 term is not 0, right?
Yeah.
Because you liked it to be there. You said that's sort of the beauty of what you are going to do. But if it's 0, then lambda can be whatever it wants to be.
That's even more depressing, yeah, because then we don't have any hint of a new scale in physics, yeah, and then maybe indeed working the medallion is the best thing to do, no?
I don't think so, but okay.
Yeah.
No. The thing I wanted to ask is the following: you made the point that you had a mapping of the various coefficients, whether you come from your WEFT or your SMEFT. I wanted to say, from the experimentalist point of view, this is one of the complications in the business, right? Because we don't know how to make the mapping.
But you don't
and
have
actually, if we ask that, we are usually told, oh, look, this is now very difficult, because in order to do that properly, you have to take into account whatever running and all these things will mix, and the renormalization here and there. And so it would be really great to know for certain things the mapping much better than we do.
No, but the mapping is very well known. So I only wrote this. This is very sketchy, yeah. So I don't want to go into details, but this mapping is known also at one loop level. We know exactly how these couplings run, how they mix during the running. The formulas are in the literature. But the point is that you don't have to, yeah. So as an experimentalist, you take this weft Lagrangian that is on the right-hand side with just 5 parameters at some specific scale, and you measure these parameters at this some low energy scale. And then you tell us, okay, this have the value. And then
but no, you don't want to end at the point where you measure some parameter. You want to be able to compare that to the equivalent parameters at high energy before you do the experiment in order to decide whether you should do it at all, right? Or whether it's already constrained.
But you can ask a theorist to do it, yeah.
Oh yes, and I told you what the usual answer is. I mean, this can be years of work, right, to really get the numbers right.
No.
I'll come to you next time.
yeah. So now there are programs, yeah, that you just it's all automatized, yeah. So people have done the work once, and then now you can use their work, and it's very simple, yeah. So for example, yeah, I don't know if there was a paper by Wouter Decken said, oh yeah, so which this.
But you see, for instance, for mu gamma, we know that since maybe 5 years only. For muon decay, it's not yet done, right?
I think that the running of the matching and running on the weft in SMEF is known complete. The complete running is known at one loop, and there's even some results at 2 loops, and also the matching is known at 1 loop. Yeah, so this is the much more is known, of course, than it's on the slides, and I think that it's in the form that is very easy to use now. Yeah, so you don't have to there are programs that automatize this, and you just have to maybe spend 1 hour to learn how these programs work, and then you get the answers. But yeah, I think it's much better than it's not so pessimistic. It's actually there was a lot of progress done